All right, welcome back. We've got a new topic today, kind of an important one, really important one actually. I have never done anything quite this important online, so I'm hoping it works out. This is kind of a test case. Um, so let me start by just doing an overview of everything you've learned in math so far. We started out before this year with 4 basic operations, so we could add, subtract, multiply, or divide. When you first started learning math, your parents started to teach you how to count. So they had this kind of like a song that they would teach you, like 1, 2, 3, 4, 5, and it didn't mean anything at first. But then they would put like a grape in front of you, and then 2 grapes in front of you, and 3 grapes in front of you, and you realized the more they counted, the more grapes you had. And then eventually they put something else in front of you, like pencils, and you realized it wasn't all about grapes, it was about how much of something you had. And then you were able to combine those into concrete operations, so these add, subtract, multiply, or divide, in order to figure out how much more of something you would have if you took these 5 grapes and added 3 more. So concrete operations are all with numbers that are given to you. And then you moved from that in grade 4 or 5 into your first algebra problems, which were problems where you had some sort of a variable, so 5 plus x equals 7, where you would use your operations, add, subtract, multiply, divide, in order to solve for x. And then from that, you came into all of your other subdisciplines, so like trigonometry or geometry, that were still just solving for x. So ultimately, your goal was to solve for a set number. And then this year, we kind of took that and added one more operation. So almost all of this year has been focusing on deriving, your 5th operation. So we can add, subtract, multiply, divide, derive. And we did a little bit of calculus. So instead of looking for an unknown value, you were now looking for an unknown function. So calculus is the study of motion. Instead of having one number times another, 4 times 8, or a number divided by a number, 8 divided by 4, we were now looking for a slope of a changing number. So that would look something like this, where I've got a function that is constantly changing. So in this case, I've got this piston in this combustion chamber from my mechanics class. You can see the distance from the top of the piston to the top of the combustion chamber is changing as a sine function in terms of time, right? So I could write that as this. My displacement is equal to some sort of a sine function where I have my amplitude times the sine of my number times time plus a phase shift. So I'm not going to worry too much about what these mean right now, but I've got a sine function that can describe the distance between the piston and the top of this combustion chamber. And if I derive that, then we'll find the slope of that function at any time. So for every time along this function, that slope is different. We learned a set of rules this year that would allow us to derive a sine function to get a cosine function. With that cosine function and multiplying by chain rule, you get the velocity or the speed of this top of the piston as it goes through the combustion chamber. If I was to derive it again, another chain rule, if I derive cosine, I get negative sines. This becomes negative. With chain rule, I have to multiply by this omega again, so I get omega squared. Gives me an acceleration of this piston. So instead of our answers being variables, our answers are now functions. That can mean something in real life. So as this distance changes, we're able to figure out what the speed is at any moment as it's changing and the acceleration at any moment as it's changing. Okay, so we went from algebra to calculus. But we're not quite done with calculus yet, even though you guys have gotten really good at deriving stuff. If I look at all of these other operations that you learned before calculus, so back in grades, really kindergarten through 2nd grade, they're all opposites. So if I'm subtracting, what we're really asking ourselves when we say 5 minus 3 is what number plus 3 equals 5. When I say 20 divided by 4, we're really asking what number times 4 equals 20. And for our final operation for this year, we're kind of going to be doing the same thing. So we'll be undoing the derivative to figure out what function, since we're not dealing with numbers anymore with calculus, could I derive to get this equation. Okay, so we can call these antiderivatives, which is exactly what it sounds like, so the opposite of derivatives. So I'm going to give our first example with power rule. So with power rule, if I was deriving 4x cubed, I would multiply by the power, decrease the power by 1, and then with chain rule, if x is a function, I would multiply by the derivative of x. So if I wanted to do this backwards, I would do all of those steps in reverse. So instead of multiplying by the derivative of x, I would start by dividing by the derivative of x. So if I do that, 12x squared dx, I'm starting with my last step and working backwards. If I divide by dx, my dx's will cancel, and I'll be left with 12x squared. Okay, then I'm going to increase the power by 1. That's the opposite of decreasing the power by 1 here. So I'm undoing our second to last step. Add 1 to the power, I get 3. Okay, then I'm going to divide by the new power. That's the opposite of multiplying by the power. So if I divide by 3, I'll get 1/3 of 12x cubed, or 4x cubed. Okay, then my last step, because if this had been 4x3 plus 7, when you derive, that 7 goes away. There is no way of knowing if there was a constant here. So I'm going to add plus c, which just means there could be any constant after that 4x cubed in our original function that we derived. It could be 0. It could be a million. We don't know. Because any constant number, when we derive it, will go away. Any questions on what I did here for this slide?
Sorry, I missed the beginning. What is it about?
As quickly as I can. So we started with 4 operations: add, subtract, multiply, divide. This year we added deriving. If you notice that all of these operations are opposite to each other. So subtraction is the opposite of addition, division is the opposite of multiplication. Or you can think of it as undoing your addition or undoing your multiplication. So 5 minus 3 is really asking what number plus 3 equals 5. 20 divided by 4 is really asking what number times 4 equals 20. Now before this class, everything that you had done up through algebra, geometry, trigonometry had been looking for a number answer. So you were looking for, before algebra, just a number. After algebra, some kind of variable, so an unknown number, using add, subtract, multiply, or divide. With calculus this year, you were looking for functions instead. So if I go to a physics problem, where I've got the displacement of this piston in its combustion chamber, so the distance from the top of the piston to the top of the combustion chamber is a sine function. It keeps repeating over and over again. If you derive that function, you'll get the slope of that sine function. So there's plenty of different slopes of this sine function as you go, right? But we learned a couple rules this year. We created a couple rules this year, or proved a couple rules this year, that when you derive a sine function, you get a cosine function. So if I do that with chain rule, I would multiply by this omega that I have here as one of my variables. So derivative of sine is cosine times the derivative of the inside is omega. It gives me a function for my velocity. If I derive that again, derivative of cosine is negative sine times the function inside gives me negative omega squared amplitude sine omega time plus phi. Gives me my acceleration, or my second derivative of a displacement, which I could measure in maybe centimeters per second squared. So our answers are now functions, not just numbers. I've got a function now that you can plug in any time, right? So if I go back, we learned how to derive this here, but if I wanted to undo my derivative, just like how I can undo multiplication or undo addition. My question that I would be answering then is what function could I derive to get this equation? Okay, so for power rule, when we derive, I multiply by the power, decrease the power by 1, and then multiply by the derivative of our inside function, which in this case is x. So I'd get, if I derive 4x cubed, I would get 12x squared dx. To undo that derivative with power rules, if I wanted to start here and figure out what function did I derive to get 12x squared dx, I would start by doing all of these, all of this process in reverse. So instead of multiplying, I'm going to divide by the derivative of x. So that'll get rid of my dx. Divide by dx gets rid of the dx. I'm going to increase the power by 1 instead of decreasing the power by 1. So that out of 1 to the power, I'm going to divide by the new power instead of multiplying by the power. It gives me 1/3 of 12x cubed. And then there's no way of knowing whether there was a constant here, because if this had been 4x cubed plus 7, when you derive it, the 7 goes away, right? So I'm going to add a plus c because there could be any constant after this in our answer. Any questions on what we've done so far?
No.
Okay. That was pretty fast. So I'm going to take a look at a couple examples for antiderivatives really quick. So if I wanted to do this one, just like when we're deriving, I'm going to look at every term individually. So this new symbol, the integral, or the integrand, tells us we're going to do the opposite of deriving. I'm looking for what function could I derive to get this equation. Okay, so I'm going to start out. Right and white over here. Okay, 1. So divide by dx. Add 1 to the power. Divide by new power. And add a constant of integration, so we have no idea of knowing if there was a constant in the original problem. Okay, so I'm just going to call on people, I think. So let's start with Kyle. Okay, for this x squared, I'm going to divide by dx, and then what's my first step? What's my next step after that?
By dx. So we add an x to x squared.
Okay, I'm going to add 1 to the power. Right now the power is 2.
1 x. Yeah.
So what should my power be here?
X to the power of 3.
3. Okay, add 1 to the power. Divide by the new power.
Oh, so 1 over 3?
Yep, so divide by 3. Okay, and then I'm going to add my plus c. Okay, then I'm going to do the same thing for all of these terms. So I'm going to jump over to someone else. Abby? Okay, I've already divided by dx for the whole equation, so I'm going to jump to my next term. This is just x, which I could say is also x to the first power. Okay.
So you add 1 to the power of x,
okay, so
x squared, and then x over 2.
Okay, over 2, perfect. And last one, so what else do I have here? I've got Aileen here. So Aileen, this is minus 3. There is no x there, so that's the same thing as minus 3x to the 0 power. So what should happen for my last term? Let me give myself a little bit more space. Aileen, can you help me out?
3 divided by 1.
Okay, I'm going to divide by 1. What's my power of x though?
1.
First power, perfect. X to the first power. Okay, awesome. So this ends up being x cubed over 3 plus x squared over 2 plus 3x plus c. Okay, again, we've got that plus c because we don't know if there was a constant there, if we're working backwards, because that constant would have gone away. Okay, we can check. If I derive this equation, I should get our what we started with. So if I derive this, I would multiply by 3 and then decrease the power by 1 to get x squared, plus multiply by 2, the 2's will cancel, x plus 3, and then my constant will go away. X squared plus x, oops, let's do the minus. It's a subtraction sign, not addition. Minus 3. Okay, so that did work, and we've got our answer. Okay, slightly harder. I'm going to rewrite this integral into power rule first, so I'm not going to integrate yet. That way we'll be ready to integrate for our next step. What else do I have here? I've got 11 people with us. I see Sarah next. Okay, Sarah, this square root of x is the same thing as what, if I want to write this to in power rule format? X to what power?
Um,
So the question is, the square root of x is the same thing as x raised to what power?
one half.
1/2, perfect. 1/2. Okay. What else do I have here? We've got 13 people now. I see. Okay, who is Gideus?
Oh, I see. Sorry.
That's okay. So how could I rewrite this 1 over x squared?
Is x power of -2. So,
Okay.
like, if we integrate, it becomes x power of -1 over -1.
Okay, you're right. Not quite there yet though, so. Okay, so this is everything that I've just rewritten. We have not integrated yet. All we've done is we've rewritten so that we can integrate. I'm going to jump over to, okay, Mick, I see you next. If I want to integrate x to the 1/2 power, I'm going to first divide this whole function by dx, so to get rid of my dx. Okay, now what do I have to do?
Sorry, can you repeat the question?
Right, I want to integrate x to the 1/2 power dx. So we said the first step would be divide by dx. Okay, the next step I need to add 1 to the power. So what's 1/2 plus 1? Okay, I'm looking for what my power should be here.
It's 3/2.
Okay, I think she dropped. Yeah, 3/2. Okay, she dropped and rejoined. So this is x to the 3/2 power, and then I have to divide by the new power, so I'm going to divide by 3/2. Okay, plus, what else do I have? I have Ninny here. Okay, so Ninny, what's going to happen to this term?
X to the power of -1.
Okay, x to the power of -1 divided by
-1.
-1. Okay, and then plus c, because that's my last term. Okay, so I'm going to simplify this. If I'm dividing by a fraction, I can flip and multiply. So this is the same thing as 2x to the 3/2 power over 3. If I'm dividing by -1, that's the same thing as multiplying by -1. So it's going to change this positive sign to a negative sign. So that's minus x to the negative first power plus c. Okay, then I could rewrite this into root form if I wanted. So this would be 2 over 3 times the square root of x cubed minus 1 over x plus c, or 2x root x over 3 minus 1 over x plus c. All mean the same thing. Okay, I'm okay if you leave it like this. But if I give you an auto-generated answer key, you might see any of these two simplified forms. Okay, and the last one. So these rules I have here are for undoing power rule. But if we have any other type of function, so if it's not a polynomial, then I would have to undo the other derivative rules. So if I want to integrate sine, what I'm really asking is, what function could I derive in order to get a sine function?
Cosine?
Okay, if I derive cosine, I get negative sine. So you're really close.
Negative cosine?
Negative cosine, perfect. Negative cosine x, and then again plus c, because we could have any constant there. Okay, any questions on what we did?
No.
Wow, okay. So I'm going to talk really quick about what this actually means. What are we doing? Because right now it's just a process. So before I talk about what our integrals mean, let me go back and talk about what our derivative means, because again, our integral is going to be the opposite. So this will make more sense. So whenever we derive our function, we were finding a slope at a point. For our units ended up being our output divided by our input, or derivative of y. Our derivative is change in y over change in x, like slope at a point. So if I had velocity, here's our function of velocity in meters per second at any time. And we'll say that function was a sine function. Then when I derive that, so that time in seconds, my answer would be meters per second. That's my velocity, or my y. dy over dx is my meters per second divided by seconds, which gives me meters over seconds times 1 over seconds is meters over second squared, or acceleration is my change in y over change in x, the slope or the derivative. Since this is a sine function, my acceleration then would end up looking like this. So acceleration, or v prime versus time, would end up looking like a cosine function. It's really the same function, but now I'm starting here at the top instead of starting here at 0. Okay. So we created a limit definition in order to get our derivative, where this is the, if I had 2 points, x plus change in x, and f of x plus change in x. Do that. So 0.1, 0.2. My slope would be my change in y, so that's f of x plus dx minus f of x, over my change in x plus dx minus x is my change in x. And if I take the limit as this change in x, the distance between them approaches 0, you get a slope at a single point, which is the derivative, f prime x, is how we started this year. Okay, any questions on what our derivatives mean? So, where they came from for our limits, or what they mean in terms of units. So we'll always end up with our units of y over x for our slope. Okay. So let's talk about what the antiderivative would mean then. So if I'm deriving, we divide our units. So if I'm doing the opposite, then I should multiply our units together. So that means our antiderivative, if I had my velocity over time equation that looked like a sine function, where velocity was in meters per second and my time was in seconds, would multiply the two units together. That's meters per seconds times second would give me meters. Or how far that we have displaced the object in a certain amount of time. Graphically, if you want to multiply x and y together, you would end up with an area. So let's say I'm going to make my function even simpler. Our velocity is always 4 meters per second. V equals 4 meters per second. And I traveled for, we'll say, 2 seconds. Okay, if I wanted to figure out my displacement, so how far has the object gone so far, I could multiply our y value for velocity, that's 4, times our time, which was 2 seconds. So I get 4 times 2 is 8. Meters per second times seconds is meters. So we would travel a total of 8 meters, which was the area that we covered underneath the curve. We're doing the same thing with integration, only now we can multiply, instead of just two numbers together, we can multiply our function together, meters per second times seconds, which means instead of just doing 4 times 2, what we're really doing is I am adding up infinitely many lines from time 0 to time 2. Which would give me the total area underneath the curve and represent the distance that we have traveled in those 2 seconds, so our displacement. Okay, any questions on what it means? I'm going to go a lot more in depth into what this looks like graphically in our next class period, so we'll work with that next week. But I just wanted to preview so you can understand how we're going to use this later. Just like what we did with our calculus stuff, with deriving, where we were able to figure out what happens with an object in motion. So this is like slope of a changing function. Our antiderivatives are going to allow us to find area, but area for a function that changes, instead of area for a function that is a set shape. So with integration, we can find the area of anything, which is a direct graphical application of integration. But it also means that we can multiply any two functions together and figure out what happens even if those functions are changing as our values increase. So integration is going to end up being used in basically every discipline that you use math for after this. So for instance, in physics, most of you are in your first year physics course, which is physics without calculus, I think. So you learned work, so that's energy, is a force times your displacement, right? So force times how far that you moved the object, F times X. But if you had a variable force, so let's say instead of just moving with the same force of 4 newtons that entire time, your force changed as a sine function. So the amount of force that you're putting into pulling a box or pushing a box is not the same. Then I could integrate your force times the infinitely small changes in x from a starting position to an ending position. And I would end up with the total amount of work that you have done. So our integration allows us to multiply functions when the values are changing. That's just one example, but any other function that you could multiply for all of mathematics, regardless of what your discipline is, whether you're working for economics or physics or anything else. If that function changes as you go, then you'll need to integrate instead of just multiply. Same thing for the derivative. Anything that you would normally divide, if your functions are changing throughout your range, so it's not just constant, then you can't just divide the numbers. You'll have to derive the functions of those numbers instead in order to get your answer. Okay, graphically here it is again. We're multiplying two parts. A change in x times a function of x, so that's like base times height for a rectangle. If I had infinitely many rectangles from x equals 0 to x equals 5, and we added them all together, so infinitely small rectangles, and I would get the perfect area underneath the curve. So when I integrate, this function is actually 1/4 x squared, so x squared over 4 in terms of x. I get divide by dx, add 1 to the power, and then divide by the new power. Gives me x cubed over 12 plus c. Okay, here's my original function. Here's what we got. If I wanted to know how much our function changed from 0 to 5, so what was the area between x equals 0 and 5, I can plug in the area I had at the end, so that's 5. 5 cubed over 12 plus c, and then subtract what happens when I plug in 0. 0 cubed over 12 plus c. And I'll get my total area between 0 and 5. Okay, 0 cubed is still 0 over 12, so this is 0. C minus c cancels out, it's 0. So I'm left with 5 cubed, which is 5 times 5 is 25, times 5 is 125, over 12 is my total area between 0 and 5. Or the exact area underneath 1/4 x squared from x equals 0 to 5. If you combine this with your linear regression techniques that we were working with last week, you can use linear regression to overlay any picture you want. So let's say here's a picture of the area in your backyard. So this is all the property you own. Draw a bunch of points there, and then use your nonlinear regression to get a best fitting